Our speaker is an android for us. Okay. We're talking about cosmology.
Hello. Yeah.
I think you can
Use this
yeah,
one.
this is laser and
Yeah.
this should be
Okay.
like forward, backward.
Yes. Ah, thank you. Yes. Where is it? Okay. Come on.
Can you try forward, backward again? I think.
Maybe something
What's wrong?
Maybe I have something wrong in my
No. That is it's always like this.
Always like this. Yes. Good morning, everyone. And first of all, I would like to thank the organizers for giving me this opportunity to come here and present my work. And I am from Center for Theoretical Physics and Natural Philosophy, High-Energy University, Naresuan campus. And it's good to come back in Naresuan because I was working here 5 years back. So it's a good experience. And today I will be talking about delta CDM. It's a name we gave to one of our formalism where we try to build models which is like a deviation from lambda CDM. And it's the idea is very simple, but it could be applied to many dark energy models. So to start with, since we have some student, I just want to spend some times in the background. Like this is I think the most famous picture in cosmology, and people have seen many times this. So you know that the universe, how it started, everything, but we are interested here. This is the dark energy dominated phase where the universe is accelerating, expanding with acceleration. And we also know the best model still we have is for dark energy or accelerated expansion of the universe is the cosmological constant. And as a historical fact, that it was introduced by Einstein himself in 1917, because the GR was giving some solutions which are evolving. So the universe was not static, and he introduced it to get a static solution for the universe. And he abandoned his idea in 1929 after Hubble discovered the expansion of the universe. And this cosmological constant again entered the current research after the discovery of the dark energy or the accelerated expansion of the universe. And this is just a recap. You know how the cosmological constant can come into the picture, that you can add a constant term in the Einstein-Hilbert equation, and then you can get this lambda here. And this lambda, when you go to the field equation level, can give you the accelerated expansion for a positive cosmological constant. And I'm going a bit fast because this is, I think you already have seen it. So this is the first Friedman equation, and this is the acceleration equation of the second one. And you can use this lambda to get a stable universe, and that was the idea for Einstein. But it is very easy to show this setup is very unstable. Like a small deviation, small fluctuation can either expand the universe or collapse the universe. You all know this behavior. But when lambda enters the back more actively in research in 1998, then it becomes the most probable candidate for accelerated expansion. And you know that now the best concordance model for cosmology has is a specially flat 6-parameter model, and which can fit the CMB data very precisely, and it's a very successful model. So considering the cold dark matter as the dark matter candidate and cosmological constant as the dark energy is the standard model of cosmology, and it is very precisely constrained by the observation, particularly CMB observation. But even it is constraint, these are the constraints. As you can see, these are the 6 parameters which are very precisely constrained. These are the different observations from the CMB, and this is the combined result from them. And you can see these numbers are quite precisely constrained. So lambda CDM fit the data very well, and this is like the posterior plot. You can go to the Planck 2028 paper, you can get this plot and table. And even the lambda fit the data so precisely, but there are some problems with the cosmological constant, and it comes from the both theoretical side and observational side. From theoretical problems or puzzles we have, that what is the why the observed value of the cosmological constant is so small. When we calculate it, it's very high from our calculation. Yes, when we represent a cosmological constant to be the vacuum energy, and this is the why the matter and dark energy density is comparable today, which is coincidence problem. And is lambda a fundamental constant or is a effective description? This you can also consider a theoretical problem. And the observational problem are coming from when we try to estimate a parameter from different cosmological parameter from different observation, and it seems the different observation giving you different result, and they are in tension. So this is, I already explained you that what is the cosmological constant problem. So the one you observe and one you calculate is the differ by or the order of 10 to the power 120. So this is huge. And this is the coincidence problem. This is also an interesting problem because cosmological constant is a constant and the matter is diluting in the with the inverse cube of the scale factor. And then we are here when this matter and the cosmological constant, they are almost same order of magnitude. If you see the picture, it's like one is 0.7, another is 0.3. If I consider both dark matter and barrier. So then why it is this equality is happening, this is happening now? Because if you plot this, the ratio, so they were like 100 orders of magnitude or 1000 orders of magnitude differ from each other, and they will be differing from each other in the future. But why this peak is here? So this is a coincidence problem, and this is maybe not only for the cosmological constant, but it's in general a problem for a dark energy models. And it can really leads to a very fine tuning in initial conditions, which needs to get this behavior at particular time. And this is the current like the current most biggest tension in cosmology, where we can measure the Hubble value from the CMB. So we are not measuring from CMB. We have CMB and we can extrapolate, and we can get the current value of the Hubble today. So this, and we can actually measure directly from the local universe. And what we find is that these two values, they differ around by now I think 5 point something sigma. So the early universe probes like CMB gives like 67 to 68, and distance ladders like the local supernovae and other observations, they give like 73 to 74. So now these results are like more than 5 sigma apart from each other. So this is a current problem in cosmology. And then another problem is the sigma 8 problem, where if you measure the S8 parameter, which is a measure of the structure you have in the universe, you find that the one you got from the Planck, which is this one, and the other one is the from Galaxy Surveys, large scale structure surveys. The posteriors have they in 1 sigma they are not coinciding. So what does it mean is that it's not that big like the Hubble tension, but it's still some like some statistically significant result that these two, the measurement from the CMB is not matching the other observation. So CMB is having lambda CDM as a inbuilt physical model in this case. And this is an updated sigma 8 is last year, and it is the picture, the new observations. They reduce the tension, but it depends on which observation you are considering. So it's not settled down that if we still have this one or not. So we might need further analysis and further observation to find this. But this is also a hint about lambda CDM going against the lambda CDM. And next come this like this 5-year observation, where they observed like 1,635 objects, and then they use machine learning and they plot this distance modulus, and what they got, they analyze all these models and in a like one by one, and then what they got, the result which I want to mention is that the equation of state they got is a bit higher than the lambda CDM. So it's not -1. So and they mentioned that it's more than 1 sigma away. So it's more than 1 sigma away means you have to consider it statistically. There is some signals. And then the most interesting one comes from the current Day5 observations, where they observe like 14 million galaxies and quasars, and they have 6 different kind of tracer to trace the evolution of the universe. And what they find is that they use this parameterization, which we call generally CPL parameterization, and it's a Taylor series expansion of the equation of state around today. And when they analyze using this equation of state, and they follow the similar like a nested kind of approach like this, like flat lambda CDM with curvature, and then the flat WCDM, and then flat W0 WA, or we call this CPL. And then what they get that the result they got is that the equation of state is having it was phantom in the past, and now it become quintessence, and it crosses in around z equal to 0.5. It crosses the phantom barrier line, which is -1, and that is a theoretical problem, because this is we know this is the region for quintessence, and this is the region for phantom kind of, like when you try to model it to some physical inline theories. So this is a phantom region and this is a quintessence region, and when the equation of state cross this -1 boundary, then you got problem in the perturbations for a single degree of freedom. So you cannot have this crossing. So your kinetic energy has to flip from negative to positive, and that will give rise to the perturbations diverging, because in perturbation you will have some term like 1 by 1 plus W. So when W is minus, everything blows up. So that is like a forbidden for a single degree of freedom. And to have this crossing successfully, either you have to build model with two degrees of freedom. One is quintessence, another is phantom field, and they separately do their like evolve, and the effective one is actually cross the boundary. So the effective crossing is not for any physical degree of freedom, so it can cross, or you have to go to some modified gravity theory. But what we in this current work which I will be presenting, we try to understand that this result obtained using the CPL parameterization. So is this parameterization has some kind of, this result is biased to this parameterization. So we tried to formalize to give a formalism where you can actually consider a equation of state from a inline physical theory. So what our proposal here is that you consider the equation of state of the dark energy is -1, which is a cosmological constant, but plus some evolving stuff. But and when delta z is 0, it becomes exactly the cosmological constant, and when it is greater than 0, it's like a quintessence like, and this is delta z less than 0, so you get a phantom like behavior. And now we wanted to check that if this delta z can be built up from some physical model like the scalar field model. So to test this approach, we first okay, this is how you can like see that when you consider 1 plus z, there will be 1 plus wz here, so that is only this delta z is controlling the dark energy sector. So if you can reconstruct this one from some physical theory, you can actually get all the observations. So when you get all these two e square z, you can actually fit it to all the observations you have. And then to have an example, like this is the simplest model we tried, and where we consider a setup where we have so it's not a quantum model. First let me clear, it's a mathematical setup where mathematically we have option of switching between phantom and quintessence by using this epsilon parameter becoming plus and minus. But this is not coming from the Lagrangian which have both quintessence or phantom. It's just at the field equation level we take this liberty to change the epsilon parameter and do the analysis for both the fields simultaneously. And what we did actually, if you do a little bit manipulation, you can write d5 by dz, and the vz is the potential in terms of this in a generic form containing this delta z. And now these are the equations for the scalar field models, and you see this epsilon plus and minus gives you, if you consider quintessence, this will be 1, 1, 1. So you get quintessence field equations for the quintessence. If it is minus, then you get minus, minus. So that is the field equation for the quintessence phantom field. And once you have these equations, and it is very simple manipulation that you have to write this all this derivative in terms of z, and then you can actually arrive where w phi, the equation of state, is looking like this. In term, this is a generic formula. It's nothing. No model is still inbuilt here. And then what we did next is that we consider this, that our equation of state, whatever equation of state we have, is in this form. And then we can find the delta z from the previous equations, and you can find the delta z to be in this form, and you can then write d phi by dz in terms of delta z. Now here we considering one approximation, which is a very physical approximation, is called thawing dark energy. Thawing dark energy means dark energy was, the equation of state is a varying dark energy, but in the early universe it was -1, then slowly it started to, when the dark energy start to evolve, then they start to dominate, it differs from -1 either way to quintessence or phantom. So this is called thawing, and this is very a good approximation because you don't mess up with the early observation because it's -1 in the early time. It's behave as a cosmological constant. So when we put these two this approximation here, and we consider that this term could be considered as a constant because this is like this is very current epoch. So it's like this is dominated by the dark energy this term, and it's not evolving very fast. So we can consider at the late time this term to be constant proportional to this, and then you can put it back to the scalar potential, and you will get the potential will be looking like this. And from here we consider that the potential general form of the potential to be in this form, some parameter a plus b delta z, because even this is a this is an approximation. So but in general form this is like you can consider this because even it says like it's only a 1 minus a 1 minus delta z by 2. So they are correlated, but even you consider them different, it's not a problem because this is an approximation. And the next one, we have a derivative in the equation. So this, even you consider them correlated, it will just vanish. And then we put it back to the Klein-Gordon equation we have here. Where is it? Yeah, you can put it back to the Klein-Gordon equation, and then you can actually find a delta z, which we started. So we started with a deviation which was arbitrary at that time. Now we are able to link to a physical theory this delta z, how it can evolve. And these are like trivial mathematics to get these things. And now how much time? 5 minutes. Okay. Okay. I think I could. Yes, I can do it. Right. Now we can actually, now once you get your equation of state delta z, you can actually form the WDE. Now when you get the WDE, you can consider this to be a fluid approximation of the thawing scalar field models you have in line. And then you can actually calculate the perturbation. These are the standard stuff. And what we did actually, we implement this in the class Boltzmann code class. And Boltzmann code in Boltzmann code class, we need to use this PPA approximation scheme just to be very give you the details, because otherwise some solutions going to close to -1, it will numerically it will blows up. So then we need some approximation which is there. We have to like switch on this approximation, and then we use the Planck 2018 full CMB SPA datasets, and they see, and these are the supernova observations, and we try to compare this model. And comparing means for the students is like not only the chi-square, getting the minimum chi-square, but there are some other checks. In here we consider the AIC, because minimizing chi-square might be misleading toward fitting a model, because if you have more parameters, then it's more likely fitting the data better. But that doesn't mean you have a better model. So you have to penalize that that thing, that your model is having more parameter than other model, which is having higher chi-square than that. And then when we did it, these are the result, which is the result is consistent, but the most interesting part is the comparison here. And comparison here, you see that this is the comparison with CPL. This is consistent with the DESI observation, because they also use this W0, WA or CPL. Our model is not favored over, the lambda favored over the lambda CDM. And this is interesting because, as I mentioned, we consider approximation which is a thawing approximation. So when you consider the thawing dark energy, it's not better fitting the data. So it's signaling what we started to see, that there might be the phantom barrier crossing, which is like is a more another proof that you might have a phantom barrier crossing, and the thawing kind of behavior might not be favored by the data. And for this model is like you can draw all these plots like the how equation of state, and you can see that the thawing behavior from the posteriors we got is actually we can get numerically also. So it shows that our construction is consistent, and this is how the potential behave. The potential is like, as you say, it's a flat, then it's tried to it evolve in late time so that fields start to roll, and you get these delta terms like try to evolve. And this is the fitting to data of AZ, and we compare with the DESI observation also, and these are all background, and this is the matter power spectrum, and you see that there are deviations from CMB because this zero line is the CMB. This is the difference plot. So there is deviation in different scale, and the deviation depends on the which scale you are. And for the CMB temperature spectrum, it actually differ significantly from the in the high L. And then what is the message here in this work is that we try to find a way where you can have a dark energy fluid description building from an inline physical theory. And we give this as an example that we consider that 1 plus delta, like minus 1 plus delta, so cosmological constant plus something as a deviation term, and then we use our formalism to get this delta. And we didn't get preference from the data, but what it means that these thawing models are not preferred by data, and probably we have a barrier crossing, phantom barrier crossing. And this formalism can be applied to the models which are more complex. So this was just we tried our first approach to get it done for a simple model. And in mind, we know this will not be preferred because this is quintessence and phantom, they cannot cross. And when you have DESI data, its preference will be always for a crossing model. So next we are going to try it for some model which can give us the phantom barrier crossing. And this is the reference. So yeah, if you have any question.
Questions?
Yes.
Thank you for your announcement.
Yeah.
As I know, all of these results were the consequence of the Einstein field equation. Why didn't you change your theory?
Why we didn't change our theory?
Yeah.
Again, can you repeat again?
As I know, dark energy is the problem of the Einstein field equation. For example, in a conformal theory, you don't have such a problem because conformal theory has a conformal symmetry, and in all of the scales, this theory very well works. Now, my question is that why don't you change your theory to other theory? For example,
yeah, the signal is here that we got something wrong. The data is suggesting it's not. Maybe we have to change the either theory of gravity or the component of the dark energy. So you can change the gravity theory, but then comes the responsibility on you to make it as successful as GR. You have to make, and you should get from the data preference that is preferring over GR. So that will give you like some robust. I think in general that's the problem with modified gravity. We have many modified gravity which can solve this problem, but they are not as successful as GR. Yes.
Actually, we know there is no any fundamental reason to use Einstein field equation because just in solar system is equation. The other is that there is no. I don't know. Still, you are in this work. in this theory.
I-
Because what is the problem with Einstein quadratic relativity? This theory is also, I think, typically renormalizable because alpha in this theory that does not have a problem with the quantum part. I don't know why don't you go to them, for example, alpha, with the Harvard gravity, for example.
For this formalism, we our actually aiming to generalize it to modified gravity other thing that why we are into this because when we see all this data analysis, they take some fluid description of the dark energy because it's easy to handle with the code and everything. And then all this fluid description comes as a phenomenologically like imposing on the as a like P is W rho. So you just consider W to be some form of Z. But our question here is that can we make this W coming from some physical theory? And this is an like minimal example we try, but next we want to try for suppose we are working on this cubic Galilean to construct this delta if we can construct it. So I am open to it, but this is not I am opposing the modified gravity, but in general this is the situation.
So I wonder about your graph about W from phantom W
Phantom to
from less than minus one
yes,
to
yes.
more than minus one. It's a like a low redshift. Yeah, you have a quintessence like that.
Yes, yes.
So it have the effect of dark energy to make the universe acceleration less than before.
Yes, yes.
Right?
Something like that you can think. Yes.
Okay, that means that means that your model or the observation make us that we have more energy density, dark energy density in the present than other model before, because to have the same amount of acceleration, we need more amount of energy density of dark energy.
If you consider this one, this is showing like the dark energy is the acceleration is slowing down in the DESI data is suggesting because in the quintessence level. So is if you see the as much you go phantom, so universe is expanding faster and faster. And for this case, it is saying that yeah, we have 70% till now, but what is the evolution trend? Is going which direction? Is increasing or decreasing? So in this case, you can see that this is like quintessence means it is decreasing. Oh, it is decreasing at this moment. But there is a one puzzle here also. This DESI data suggests this to be the crossing and the current equation of state to be quintessence. But when we try to solve the Hubble tension means a high value of Hubble. So it should be more than lambda CDM. So then your equation of state has to be here in the phantom today. And we don't know how to solve these two together. These two together solving is like they are opposite demanding situation. Yes.
Yeah, another question is about something like error bar. I mean, I'm not sure this is an error bar, but
Yes.
the shaded with green
Yeah.
that is looks larger and larger.
Oh, yes.
Yeah. It's a form experiment from observation, right?
Actually, these are observations. These are what they did in DESI. They have a redshift bin, and they bin it the observation and find the equation of state only for that redshift evolution. And they have another bin here. And as you go farther, your experiment and observation has more errors. So you get like more error bars there.
Yeah, but I think when we have at very low
Yeah.
C,
Yes.
We have some the effect of something like peculiarities of accuracy rotating around. So it can make
Which one?
more
Which one again?
peculiarity.
Peculiarity. I think they correct it. They can correct the peculiar veracity.
Yeah.
And then they can give you after correction the result. And because when you go further, your distance ladder, each distance ladder has error adding up. I think for one by one it is adding up. And for this one is like, this is from the MCMC chains. You can generate this plot. So this is MCMC have a base fit, and you plot the base fit along the redshift, and each redshift your base fit evolution has a error bar. And this is not observation. This is from MCMC analysis, statistical analysis. And since you are using the low redshift data, as far you go in the high redshift, your MCMC chains will have more statistically like more fluctuations there. Yeah.
I'm not sure I'm correct or not, but in your words, you try to represent the scalar field energy by fluid. This is correct?
Yes, yes.
Okay. So now my question is, when you derive the derivation equation, you use speed equal to 1, right?
Yes. No, I think we consider the fluid sound speed. There. Yes. So we get the fluid equation of state, then we consider the perturbation as dark energy as a fluid, not as a scalar field.
But you try to mimic quantum model, right?
Not quantum, Thawing quintessence or Thawing phantom. That's why, because it's not a quantum, it cannot cross. So we get the lower evidence by the data.
Okay, but in your case, you use the single fluid.
Single fluid.
Single fluid.
Yes.
So when you derive the derivation for single fluid, and then W plus minus 1, this is free from the.
No, it is not in general free, because when we consider for our model, we try to keep the equation of state we get here. It can cross in general the phantom barrier, but since our inbuilt model is a thawing type, so we choose a prior on W0 minus negative, this one, so that it cannot cross it. So first thing that we impose this to be consistent with the model, the physical model we are building, and then since even it cannot cross, and as I was mentioning, we here you will have a problem W equal to -1. But even this model is not crossing. In the early time, we said that this equation of state will go to -1. Then you will have the same problem. So that's why we use this PPA approximation. This is the approximation scheme to make the fluid cross the phantom barrier without diverging the perturbation. This is given by Antonio Luis from the same guy who did the Cosmo MC, who wrote the Cosmo MC.
I will discuss with you about
Yes, yeah.
I never know.
Yes, yeah. Thank you.
Any more questions? Maybe the last one.
Yes.
How can you try to model the potential in terms of scalar field? Because I think you have in terms of the range,
Yes.
and then can you model?
That we are trying the reverse. We are trying to do it reverse way. Like now we are thinking to like consider this delta Z to be some known parameterization like CPL, and then we want to construct the equivalent theory, like then we'll get from. So now we are starting from the field equations of scalar field, then we are getting delta Z. So we are trying to do the reverse process where we put the delta Z as CPL, then integrate it back to the V phi. So if we get this, then we can claim that okay, this physical setup is the equivalent in this theory to the CPL parameterization, and we can study all the microphysics or physical things we can have. Yeah, we are trying that.
not easy.
Not easy. Yes, yes, you know, it's a reverse problem.
Okay, so let's thank Nandan again.
Thank you. Okay.
Thank you. You can just.
Hello, hello.
Okay, for the next speaker, we have Vijay from IF. He's going to talk about the Hamiltonian analysis.
Okay, thank you.
Can you test,
Hello.
your
Ah, right, left. Okay. Okay, so actually, I work in string theory, so I'm trying to look for something that might be quite match or related to this school. So I extract part of my paper and then give some detailed analysis on quadratic duality symmetric action. So actually, in my work, I do nonlinear action and then also extend to describe the brain, but we are not going to discuss them here. Okay, so as I mentioned that I have simplified from my paper, so there will be not many citations or maybe none at all, and then I have skipped many topics. But if you are somehow interested, you can check on my paper. Okay, so I will talk about first motivating the duality symmetry, and then talk about the linear twisted seriality in the sense formalism, and then just try to see what the action would look like, and then do the Hamiltonian analysis, and then give you the takeaway message. So as a motivation, so what is a duality symmetry? So let's just consider Maxwell equations in free space. And this is invariant under the duality transformation from E to B and B to minus E. Or we may make an SO2 duality rotation, some inner rotation by having this matrix multiplied, and then you will be able to see that Maxwell equations in free space is still invariant under this. But on the other hand, if we look at the action, then where E and B can be written in terms of A0 and vector A. As Dr. Pongwit has already told you from the first day. Okay, so if we vary the action, so basically this is just pretty much repeating what Dr. Pongwit said. So if we vary the action, then we get the two of the Maxwell equations. Sorry, these are the equations of motion. But these two equations are what you get for free, which are called the Bianchi identities. Okay, so we have got 4 Maxwell equations. 2 comes from equation of motion, 2 comes from Bianchi identity. Okay, but if we try to apply the duality symmetry directly to the action, then we see that it's not really a symmetry. So a natural question is that can we make duality symmetry also at the level of the action? And the quick answer is yes, and it has been done in many papers in the past. Okay. But the idea is that the main idea is to introduce extra pair of electric and magnetic fields. And we will first discuss at the equation of motion level how to do it, to introduce it to the other pair. So we define the other pair of electric and magnetic field, D and H, in this way. And then the relationship with the new pair, with the old pair, is called constitutive relation, and we may define the dual pair of the potentials C0 and vector C, so that the D and H automatically satisfy the Bianchi identity. And also we recall that we also have the other Bianchi identities from E and B. And actually all these four equations are Maxwell equations without having to use the action. And if we look at the duality symmetry, then the equations still have got duality symmetry, the SO2 duality symmetry. And yeah, before we go to action, let's do the nonlinear generalization. Although we are not going to discuss much, I mean, in this talk, as actually this is the only thing that is having the word nonlinear, perhaps. So in order to generalize to the nonlinear theory, the equation, the constitutive relations are going to be modified, but the Bianchi identities are going to remain the same. And it is convenient to work in the define the F mu nu and G mu nu, and along with the A and A hat. And for linearity, for the linear theory, the constitutive relations is just that F is equals to 1/2 epsilon mu nu rho sigma G rho sigma. So it's actually F is equals to the dual of G, basically. But if we want to do the nonlinear generalization, we don't just try to just put some functions of nonlinear functions of E and B's, and then we will get no. Yes. A hat. So actually, from here we have defined the other pair of electric and magnetic field, and then we have defined the dual gauge field, which is C0 and C. So basically, actually, C0 and C is A hat. I mean the extra gauge field, basically. Yeah. So in order to do the nonlinear generalization, we need that the constitutive relation to still satisfy this Galois-Sumino condition. Okay.
How can we use C as gauge field? Can we validate?
We define the H and D in this way, related to the C's, which is in a similar way as how E and B are related to A. Yes.
Something like emergent, something like
I'm not sure if it's an emergent, but I'm just thinking that it's just a way that we try to introduce the extra pair, so that at the equation of motion level, we actually don't need the equation of motion of something. So actually we get equation 9 and 10 for free, basically. And we may do some other generalizations, for example, coupled to curve metric or coupled to Axion and Dilaton. And in this case, duality symmetry group is going to be enhanced from SO2 to SL2, R. And we may also couple to the two form sources, where in the context of D3 blend, this is just the Karp-Ramon and Ramon C field in supergravity background, but don't need to care about this much, because in this talk we are just only going to discuss the linear theory, and that is coupled to curve metrics. So there are two main strategies in the literature. The first one is to construct an action of A and A hat, and such that we get constitutive relations as equation of motion. As you recall that we get the 4 Bianchi identity for free, so the constitutive relations have to come as an equation of motion. And this is one of the standard strategy and is made possible by the PST formalism, and also possible to construct and extend to further, but we are not going to discuss this strategy here. Actually, we are going to discuss the strategy 2, which is that we construct an action with F and G that they already satisfies the constitutive relations, and at the equation of motion level, we then realize that F and G can be expressed in terms. F and G are field strengths at the equation of motion level. We realize them as field strengths, and this approach is made possible by the Sen formalism, which is relatively more recent. And in this formalism, actually, even F and G are not independent fields. In the sense that they are composite field, we don't vary with respect to F and G. There are some other there are actually some field that is an independent field. We vary with respect to them, and then we can construct F and G from them, for example. And then this theory also contains a gauge degree of freedom, and it also contains 2 metrics. One is the standard metric, and the other coupled to gauge. Yes.
Recently, a paper was appeared on archive by Milton. He said there is no any more ghost in high-curvature theory of gravity because ghost does not relate to the energy of the particle. It's related to the norm of state, and in Hilbert state, we know norm of state always should be positive. But in Crane space, since Crane space has a causal structure, norm of state can be negative. Therefore, there is no any work was in high curvature theory of gravity.
Yes, thank you. So actually, so my work is actually about basically electric magnetic field coupled to external gravity. But of course, that we would, talking about ghosts is something weird. But in this formalism, actually, the ghosts are, I should have mentioned that the ghosts are going to be decoupled, completely decoupled from the physical sector, and we are actually interested in physical sectors. So as long as the ghosts remain in its sector, we should be fine. Okay, so the paper goal is to keep doing the extension, but in this talk, I will just describe the linear system in the curved space-time and then describe how to apply the constraint analysis on this system. And the physical system, or if we consider the on-shell consideration first at the equation of motion level, so we have got the physical sectors which are the gauge field and the dual one, which are collected into the doublet. And it is coupled to a physical metric G mu nu. And also we have got an I-physical or the gauge sector, which has got the other gauge doublet and is coupled to I-physical metric G bar mu nu. And actually, it is also possible to include other external fields, but we are not going to discuss them here. And okay, so for the nonlinear theory, the physical field strength doublet, written as a vector F, it satisfies the twisted self-duality condition. So F equals to star F, where star here is the hot star, along with some 2x2 matrix of epsilon ij. Okay, and then and this twisted severability condition is equivalent to the constitutive relations, which is actually F mu nu equals to 1/2 1 over square root minus G epsilon mu nu rho sigma F hat rho sigma. And at the action level, the independent fields are actually consist of one form doublet. I mean the vector P, where they have got one index. Okay, most of them has got one index and two form doublets Q. Okay, two forms mean they have two index and antisymmetric, and such that it satisfies the twisted self-duality condition, but in basically in the unphysical sector, where star bar is the unphysical hot star along with the 2x2 matrix of the epsilon. And we have got the composite field which constructed out of Q and G bar, which satisfies the anti-twisted self-duality. And then we have got the composite field H, which is equal to Q minus R, satisfying the twisted self-duality condition in the physical sector. And the action is, I mean, can be written down is actually already, I believe that is pretty much already in paper by Professor Sen. The original, one of the original paper already. So yeah, just don't worry about what it looks like. But the idea is that we have got the PI and then QI, and then RJ is in terms of QI, but the Q is subject to a condition. So we can use this condition to eliminate the Q hat. We may or may not want to do this, but if you want, this is the form of the action. And the action is invariant under the SO2 transformation. And if we consider the equation of motion, so this is, I mean, the P and Q are the fields that we have to vary. And then this is the equations of motion. And then if we integrate this equation, we get the arbitrary function psi, which satisfies this equation. And then we can work more on equation of motion to get the equation 24. I'm not going to give the details, but the idea is that we are going to isolate the physical field, which is coupled to the physical metric through the star. And the unphysical field, which is going to couple to the to the unphysical metric through the star bar. And actually, at the level of equation motion, we can only talk about whether the fields are uncoupled. In order to say whether they are actually ghosts or not, we have to check at the equation of motion. Sorry, have to check at the Hamiltonian analysis, at the Hamiltonian level. Maybe you have already learned this before in Professor Babichev's. So let's us now work on the Hamiltonian analysis. So let's us rewrite the Lagrangian in a more ready form. Still not really totally ready, but this is the form that is going to be useful. And the first space variables are the Pi mu and the Qi subscript ij, because we have to use the twisted severability condition to restrict some of the components of the Q, so it's not totally in the have the mu nu. So we have to trade away the 0i components, basically. Okay, and the space-time matrix, I mean the unphysical metric G bar and actually the physical metric are hidden in R, in big R here. Okay, so these space-time metrics are external fields. So we just follow the process of Dirac-Bergman analysis. So algorithm. So start from working out the conjugate momenta of the P. Okay, so the zeros component of P and the space component of P. So then we look for the conjugate momentum for Q. So actually Q, the Lagrangian doesn't contain Q dot. So this is the conjugate momentum. So basically the primary constraints are that pi I0 is equal to 0. And the pi ij I subscript I is equal to 0. And it would be convenient if we now, if not already, to do the ADM decomposition on most of the metrics, and then we write the total Hamiltonian. So now the total Hamiltonian is in the form of the lab chips and the 3D metric for. I mean, maybe from here it's still not so clear that we also have this that we also have the physical metric, but we do have it hidden. Okay, for example, within H. Okay, and then we just work out the preservation of the primary constraints, and then we get the secondary constraints, and we keep on doing. But it turns out that these are just all we get up to the secondary constraints, and then we reclassify to get the first class constraints, which just looks like the constraints for the Maxwell series, but we have got a pair of them. I mean, the index big I is from 1 and 2, and we also have the second class constraints. And then in order to kill the first class constraints, we impose gauge fixing conditions, which is just basically the Coulomb gauge condition on each of the of the eyes. And just a note that the Coulomb gauge condition is not covariant, because I mean if it were covariant, we would be asking what is it? I mean what is the metric that we use to raise the index, because we have got two metrics. But it is not covariant, but they can be used to eliminate the first class constraints in the standard way. Okay, in the standard way as in Maxwell series, so that now all of the constraints becomes the second class constraints, and then we can solve all these. I mean, having only got just the second class constraints, we solve all these to eliminate some components of the phase space variables. And okay, we eliminate these and also eliminate longitudinal components of pi and p for each eye. And in the reduced phase space, the Hamiltonian is separated into the two sectors. So there is an unphysical sector contains all the unphysical fields. I mean in order to say that it is unphysical is because it contains the wrong sign of the kinetic energy. Okay. And whereas the physical Hamiltonian is positive, I mean positive in kinetic energy. Okay, so so in the gauge sector we have got this field, which is unphysical and is coupled to the G bar. I mean this is unphysical because its kinetic energy is negative, whereas the physical sector we have got this one and is coupled to the physical metric. And yeah, just quickly come to the moral of the story is that when you construct action, you would want to make sure that your action satisfies all the required symmetry, and also it should reduce to some equations of motion that you expect, or maybe give you the dynamics that you want. And then the lesson, especially from the Sen formalism, which again I'm not sure if it's going to be relevant here. The gauge fields, I mean the action in the Sen formalism is that the gauge fields are not independent fields. The field strengths are also not independent fields. They are composite fields. And also that gauges are not always bad as long as they are completely decoupled. And in order to discover ghosts, at least the type that comes due to incorrect sign of kinetic energy, we are not able to discover it at equation motion level. We have to do it at the Hamiltonian level, which is also maybe the fact that you have also listened. And in order to see how ghosts get decoupled at the Hamiltonian level, you might see it after you do the gauge fixing to eliminate all the first. By eliminate, I mean change all the first class constraints to second class constraints, and then after you have all the second class constraints, you solve for the second class constraints to reduce the phase space, and then only at this level of reduced phase space do you realize that the ghosts are decoupled. Yes, and this is all. Thank you.
If I want to ask that if we have something like duality symmetry in the level of the action, why is it important?
I believe
I just,
yes.
think that you said that something like we have no symmetry duality at the same level of the action, right?
Originally, yeah. I mean, for the standard Maxwell action, for example, or DBI action, we don't have duality symmetry at the action level. But
How can you see that? I'm not sure that this part. Could you explain why we have no that?
Okay. So, for example, the simplest one is that if you change from E to B and from B to minus E, then you see that the action changes from S to minus S. So it's not really having the duality symmetry at action level. But or more precisely, you can try this.
So SO2 is something like you think about E and B is
yes, like this. Yes, at the doublet, yes.
And yeah, transform each other. Okay.
Yes.
And why do we need to have symmetry duality at the action level?
Okay, good question. So actually, the only thing I know and not more is that I believe that if we want to do the path integral quantization, then we want the action to have all the symmetries that are available.
And it's important in your work about D3A, if we have symmetry duality?
Is it important? Not really, but I mean, if we want the discrete action that is that is duality symmetric, then yes, this is one approach to do. You can do it through the PST approach also.
It means that if you have particle formation and you have symmetry, this you can work on it in particle easier, something like that.
Yeah, I believe so, but I don't work on path integral myself. Yeah, so that's all I know. Yes.
And another question: what is the
Twisted self-duality condition?
Yeah,
Okay, very good. So basically, this is just the duality of G, right? I mean, but F is related to G. So I mean, if this were the G, then this would have been the G would have been self-duality. But we have to twist it because mathematically it is not required the left-hand side to be G. We have to have two fields. And then they have to be related. I mean, we apply the duality, the Hodge duality basically, and then we have to apply the epsilon ij matrix. So you think of E goes to B, B goes to minus E, that kind of stuff. Yeah. So the twisted self-duality or twisted duality is that it consists of the standard Hodge star, which normally is the star, but I denote it as bullet. The standard Hodge star along with the 2 by 2 matrix of epsilon ij.
So it have nothing to do with twister theory at all.
I from what I know, I guess not, but maybe I might be missing something. They might be really related. I don't know, really. Good question.
Do you think it is important, generally speaking, if we have a certain symmetry at the equation of motions level, is it important to have the same symmetry in the action level as well? Is that always the case?
I can only hope so. Yeah, I mean, if we want to do the quantization in the path integrals, I mean, repeating this story, then I hope. Yeah, I don't know more
Oh, okay,
to say more.
thanks.
Yes.
So I wonder about symmetric duality at
Yes.
the action level and non-action level. I think if in the classical level, it might have the same equation of motion or the same effect, right? It can have the same equation of motion in classical level. Between you have circularity at action level and non-action level.
Yes, I believe that we should always get the equation of motion that is duality symmetric.
Yeah.
Yeah,
But in quantum level, it might be something like classical level is the same, but in quantum level, it have something that different. Is it possible?
yes, I think so, and it doesn't prevent the path integral, the action appearing in the path integral to have duality symmetry. I mean, even if it's going to break or not at the quantum level, I believe that at the starting point you still have the action that has got this symmetry.
What about something like quantum anomaly? Yeah.
Yeah.
About something that relating to the quantum concept current.
Yeah,
I'm not sure.
yeah, I don't know, but I would still guess that this is still the starting point if you want. Yes, yeah. But there might be other approach. I don't know.
And for Zen formalism, what kind of the system or the application of Zen formalism that we can use to work for?
So actually, the original paper by Professor Sen was to construct, if I recall correctly, type 2A or 2B supergravity theory. Yeah, so it's in another formalism, and is his motivated from string field theory, and yeah. So, but the other applications is that because this formalism is really useful for what is called self-duality theories and duality symmetry theories. So we can use them to construct actions of these theories.
Yeah, I think let's thank teacher again.
Thank you.
Okay, good morning, everyone. So the next speaker is myself. So I'm Supakchai from High-Energy University. Today I'm going to talk about my works with David from High-Energy University. So basically I'm going to talk about black holes and dark matter. And this talk is based on this paper, which is just available on arXiv. So the plan is 3 parts: introduction, and then I'll talk about the black hole solution itself, and then the last part is the conclusions. So basically, in this work, we consider a static and also rotating solution with a dark matter profile called the Denon. And after we obtain the black hole solution, we perform some analysis on scalar perturbation on this background. As you probably know, that we have plenty of evidence that supports the presence of the dark matter from the small, probably like the smallest scale at the galactic scale. We have the proof that the galaxy rotation curve doesn't behave the way that we expected, and one of the explanation is there should be some missing mass in the galaxies to compensate this difference. For a more larger scale, for example, the galaxy cluster. So here's in these figures, we have 2 galaxy cluster moving past each other, and when 2 cluster moving past each other, the pink region or the violet region in the middle is the part where the gas of each cluster like interact and heat up, and then it emit X-ray. So this purple violet region here is denoted the part of the space where there's a strong X-ray emission. However, when we actually map the mass distribution of the whole process by the gravitational lensing, we found that the majority of the mass is not in the hot gas, but is in the left side and the right side of the photo of the pictures here. And if we just counting only the visible part of the mass that we can see, that does not add up with the lensing that we observe. So again, another evidence that there must be some missing mass from this. And the last one is from the Planck observation, where when we model our universe with dark energy and dark matter, we find that the observation and the prediction from the theory mesh very, very well. So this is another simple evidence that suggests that okay, dark matter should be we should looking for the dark matter. So I took this slide from Patipan Mosawa because I really like his introduction about the dark matter. So what we know so far about the dark matter, beyond that, it is just some kind of the missing particles, missing mass in the universe. So we know that it must be massive because it interacts gravitationally. It should be electrically neutral, so that means it doesn't interact with any electromagnetic radiation, and it should interact weakly with normal matter, and it should move very, very slow or cold, and also it should be stable on the cosmic scale. So that means it should be there like really, really long times ago. However, when we looked at our standard model particle, we don't see any kind of fundamental particle that has all of this property. For the mass, so for the massive, then we can rule out like gluon and photon, so that they cannot be like the dark matter. Electrically neutral means that they have no charge. And for the stable one, we know that the Higgs, the scalar Higgs cannot be the dark matter as well, because Higgs itself doesn't, it's not stable. So none of these fundamental particles that we know have all of this property that we want. So it must be something else. However, before I move further in my talk, I would like to say something a little bit about the cold and the warm dark matter first. So basically, if the cold means that the dark matter, the particle of the dark matter is moving very slowly, that it means that comparative to another model, the warm dark matter is the model that we model the dark matter particle move slightly faster compared to the cold one. However, those two models also pose the problem by themselves. For example, for the cold dark matter, there's something called the missing satellite problem, because when we model the dark matter with the cold dark matter model, it predicts that there should be more dwarf galaxy orbiting, the large galaxies. So this is called the missing satellite problems. Another one is it also predicts the core cups problem. Basically, it's predicted at the center of the galaxies. The density of the dark matter should be like really, really high, because it's moved very slowly. So it has, it can be attractive to each other very easily and then accumulate, especially at the center of the galaxy. The warm dark matter kind of like make the core cup problems more less worry, because now for the warm dark matter, the particle move a little bit faster, so they do not accumulate very well compared to the cold dark matter. So that might somehow solve the core cup problems. However, with the slower clumping matter, it makes the prediction that then the first star and the first galaxy in the universe should form much later than we observe. So that's another problem with the warm dark matter. But well, in my talk, I will particularly focus in the cold dark matter model. And okay, this is the picture of the supermassive black holes, which I believe that I don't need to convince you guys that they are real, they exist, right? So I'm gonna skip this. So basically, my works we just consider how black holes and dark matter like interact to each other, because we see that we observe that there is a supermassive black hole at the center of the galaxy, and we know that rather than supermassive black holes, we also have the dark matter halos too. So somehow they must have some interaction to each other. So the first question that we could ask is, so then how we do model the dark matter without knowing the particle physics property of the dark matter? So basically, we model it by using something called the density profile. This is just a mathematical function that describes how mass distribute in the galaxies. Probably the most well-known one is the Naresuan White profile. It is, we obtain this profile by doing some large n-body simulation in the computer. And from the start, we found that the Naresuan White profile also gives us the cups profile. That means it predicts that at the center of the density profile, the density of the dark matter should be really, really high. Okay. However, the observations seem to suggest that there is no like spike, or there is no very, very high density of the dark matter at the galactic center. So we, rather than looking for a core profile instead. And even worse, when you add the supermassive black hole at the center, that even worse, because the gravitational pull of the black holes at the center like keep extracting more and more dark matter particle toward the center, create what astronomers call spike, which is basically is the phenomena where the density at the central region is going very, very high, since more dark matter is, get attracted toward the black holes at the center. And if that's the case, that means dark matter annihilation rate, if the dark matter particle do annihilate, must be like extremely increased, because there will be a lot of activity of dark matter particle going on around the supermassive black holes. So we should be able to observe the end product of this annihilation very, very easily when we looked at when we look very close to the supermassive black holes. And also, more dark matter at the center should somehow change the dynamics movement of the star moving close to the supermassive black holes too. And this is a profile that I'm going to consider. It's very generic, a general profile. The ρ0 is the density profile at the center, and R0 is just the length scale of the dark matter halo. And there are also 3 more parameters, alpha, beta, and gamma. So we call this, not we, somebody else, but people call this as a double power law. And it's very general because it can give rise to many, many type of dark matter profile that are already out there in the market. For example, if you want to call profile, you simply get, these 3: Burkert, perfect sphere, plumber sphere, and so on. That list is go on and on. The number behind it just is a short, is a notation that, that means the alpha is number 2, beta is number 3, and gamma is 1. So basically in my talk, if you see like 2, 3, 1, that means I'm setting gamma to 2 and beta 3 and gamma to 1, so on and so on. On the other side, we also have another kind of density profile that create a Kapsky profile, and the list is like this. And among all the profile that I'm going to talk about, I'm going to focus particularly on the Denin 1,4 gamma. Okay. So now, if you try to understand this density profile a little bit more, first we can find the mass function of this density profile by integrating the density profile by this integration. And it turns out that the mass function is proportional to 1 over gamma minus 3. That kind of prevents us from setting gamma to be 3 because it gives unphysical mass profile. And also, as you can see from the profile above, when I is go to infinity, the rho is goes down as 1 over r to the 4, and at the center, the behavior of the density function is behave as r to the minus gamma. So gammas control how steep your profile is, especially at the center. Among all of these arbitrary numbers, when gamma is 0, it gives us a core profile. That means you have a constant density profile at the center of the Denin type. Okay, this is I'm talking about, and the reason that people start to becoming interested in the Denin because it's very flexible. Because rather than the only exception is you cannot set gamma to be 3, but other than that it can be any numbers. Okay, historically speaking, the Denin profile actually was developed by the Denin. That's the name of the author. And actually, it was proposed to explain how light distribute in the galaxies. Okay. Cup.
I just wonder why the mass that not depend on R.
Oh, I just write it in. Oh, depend on R. Yeah, it should, but I forget to put it here. Yeah, but anyway, the mass will be diverged when you set gamma to 3 anyway. So, yeah, that's how it is.
But if gamma is less than 3, so it's become negative, right?
The negative.
So we have
I also hide the negative number as well.
Really, huh? Negative.
Yeah, because this is just a proportion.
Yeah.
Proportional to, right? So actually, I don't remember the whole formula exactly, but there should be somewhere that the negative side can be absorbed too. Yeah. I just want the only reason that I just put it here because I just want to emphasize that gamma is gamma equal to 3 is forbidden. That's all. But the rest is okay. Okay, I'm going. Okay, and then a couple of years ago, people start to model, become interested in the what is called the outer faint dwarf galaxy. So basically, it's a very very small galaxy where the luminosity is very very low. Basically, the outer faint dwarf galaxy has the radius is about nearly 100 light year, and luminosity is 100 or 1,000 times the luminosity of the sun. So it's very, very dim galaxies and also very, very small. So before this, people believe that the dwarf galaxy cannot host a supermassive black hole because it's too small. But then somehow we managed, not we, but some astronomer managed to confirm that actually for some dwarf galaxy, it is possible to have the, not supermassive, but very, very high massive black holes, and also in some case, supermassive black hole at the center of the dwarf galaxy. So then people start to use the Danian profile particularly to investigate the outer faint dwarf galaxy because compared to other kind of galaxy, it has the highest ratio of halo mass to baryon mass ratio. So basically, the faint dwarf galaxy has has dark matter very very much more compared to the to the other type of the galaxy. So it's very good laboratory to explore the idea about the dark matter. And this is the list is not stopped like just this, but this is just the list of the paper. The red is the number of the archive, the archive numbers, where people construct black hole solution using, following all this profile. Okay, and what I'm going to do here, so basically in this work, we construct static and rotating black holes with the double power law profile. That means we keep alpha, beta, and gamma arbitraries. And so for the spherically symmetric solution and also the rotating solution too. And after we obtain the solution, we compute the quasi-bound state and amplification factors, which is related to the energy extraction process of a rotating black holes. So we start with the basic spherically symmetric background, and we model the dark matter to be in the anisotropic fluid, where the T mu has only like the diagonal component, rho density, radial pressure, and tangential pressure. And from the Einstein field equation, we obtain these three components, where the first, the time and the radial component imply that rho dm and PR must be, must satisfy this red color relation. And the next step is we replace rho dm with the double law profile. This. So number 6 is just another way to rewrite the temporal component of the Einstein equation. When we put 7 into 6, we can basically solve for f, which is it gives us the closed analytic function. Looks horrible, but analytic. Where the metric function itself described by the so-called the hypergeometric function, and and we keep alpha, beta, and gamma like arbitrary at this point. Rs is just another integration constant which we will set to 2m, because we want this function to get back to the Schwarzschild form when we switch off the dark matter parameters. Yes. No, just this.
But if you explained in last time.
Mm-hmm.
You should have some structure from the last
Oh, you mean this?
yes.
Yes. Because you remember we can.
Therefore, RS, you can put RS equal to 0. Why do you keep RS?
Because otherwise, if you set rho 0 to be 0, then it goes to asymptotically flat. Sorry, it goes to Minkowski space because you only have one.
No, RS, you keep RS non-zero because you are to obtain singular solution. Yeah, because
Oh, yeah, I know what you mean.
yeah.
Yeah, but please.
I think M has some contribution from the last term.
So the last term we can rearrange the last term such that we can transform the rho 0 to be the mass of the dark matter, purely the mass of the dark matter itself. So that's possible. But then the reason we keep it like this because we didn't think much about the singular or regular black holes at this moment because we just want the number 8 to reduce the Schwarzschild form when rho goes to 0. That's what I mean.
I thought,
What?
the last term we just contribute from the dark matter, so that it's outside, far away from the horizon, so that you get this part off, so that you recover Schwarzschild in this. No, I think it's so far from horizon.
Yeah.
It should be because
Yeah.
the dark matter will handle it.
In infinity, you have an object in the center. This object has some mass. And that object has some contribution from the dust.
Mm-hmm.
Non-zero RS means if you have a singularity, the center of your solution, you have an infinity point like that in the center of black.
Of the
Yeah, that's all it is. And you go.
So you say that we don't need the RS.
But if you don't have dark matter handle,
Yeah, you get nothing.
you cannot just a fact. For example, you said rho 0 to be 0. That there are no dark matter.
For us, I think I think it makes more sense if we kill off the dark matter term and then we still have the black holes. That's what we mean. Yeah. Okay. Maybe we can. Yeah. Oh, okay. I'm running super late right now. So, but as a trade-off, of course, the PI and PT must be put into this horrible form. But then, after we obtain number 9, number 10, this solution will be the solution of the Einstein equation automatically. And this is the f function plot as a variation of gamma. Remember, gamma is the Dehnen profile parameters, where the gamma control the stiffness of the diameter profile, and we see that there's only one horizon, and it's asymptotically flat because it goes to 1 when r is very, very large. And we compute some curvature singularities. This is the Ricci scalar r square and the Krishman scalar, and also these curvature scalars go to 0 when we go very, very far from the setup. Okay, the next part is I'm going to talk about in the under 6 minutes, which is how we construct the rotating solution. So basically we use we not exactly solve the Einstein equation in this case, but we use the so-called Newman-Jennings procedure. where it can be described by this schematic in a schematic way. So basically, you start off with the static C matrix. This is the F function that I just showed you earlier, and then through some transformation, we can find the rotating counterpart of this C matrix. If anyone wants to know more details, you can come and talk to me later. I'm going to skip this really quickly. Eventually, we can obtain a curl-like rotating black holes as the equation 13, where the black hole and dark matter spherically symmetric profile is lying hidden in this function. The F here is the spherical symmetric static solution that we talk about later on, and of course this solution reduce smoothly to Kerr and Schwarzschild black holes as we expected, and also when we set spin to 0, it gives back to the spherical symmetric solution that we just discussed earlier. And this is a plot where we show the extremality of the solution. So basically, this line represents the extremal limit of each case. So you can see that this is where we vary gamma parameters. The meaning of this figure is, for example, when gamma is 0, if you move along this line, you will get the extremal black hole, because rotating black hole usually have 2 horizons. Above this, no horizon. Under this curve, you get the 2 horizon black holes as usual. So that's basically the meaning of this plot. And I'm come to the last part of my talk, where we consider the scalar perturbation. So basically, we solve the Klein-Gordon incurved background with the rotating black holes. And for the rotating one, the angular equation and the radial equation looks like this, where number 19 and 12, they are linked by the separation constant lambda. Okay, so since I'm going to talk about the quasi-bound state, I think it's better that I give you some idea about what quasi-bound state is. So this is the table compared to the difference between the quasi-normal modes and quasi-bound state. So basically, for the quasi-bound state, the big difference comes from the boundary condition at the infinity. For the quasi-normal mode, basically we require the only outgoing wave at infinity. But for the quasi-bound state, we demand that the field should be like decaying exponentially, where the little m here that you see here is the mass of the scalar. So for the quasi-bound state, the minimum requirement is you need the massive field. And the picture is quite different, because from the quasi-normal mode, the decaying rate tells us about the ring down of the perturbation, where because it's oscillating and decreasing over time. Sorry. Where the quasi-bound state is more like a bound state that we see in our quantum mechanics class, like in hydrogen atom. So basically, for the quasi-bound state, we can picture as the field that we use to perturb black holes somehow keep trapped within the gravitational potential of the black holes. So the field bound by the black hole's potential will for the quasi-bound state thing. And since we are going to do some analytic work, so it's better we put some assumption onto the system. For example, slowly rotating. So we consider only when A or spin parameter is very small. In this case, in particular, we can approximate that the separation constant takes just like in the spherical symmetric L times L plus 1. And we're going to solve for the quasi-bound state frequency by the analytic method called the asymptotic matching method, which is basically we start off with the radial wave equation. We consider the radial wave equation in the very large R limit and very near the horizon, and turns out that we can obtain a useful radial wave equation at each side. For example, when R is very large, this is the new radial wave equation at the very large R, and we can solve this equation analytically to obtain it turns out that the equation itself satisfies the conference hypergeometric differential equation, where we can write down the general solution like this. On the other hand, we do pretty much the same, but it turns out that it, rather than being confluent, but this time is hypergeometric differential equation. After we obtain these two solutions at both sides, then we match in the intermediate region. And by matching that, we obtain this analytic formula for the omega. One thing that I like to emphasize is this is the real part, and this is the imaginary part. So as you can see, the side of the imaginary part depends on this term, the term that I highlight, which is actually satisfied by this so-called superradiance conditions. So basically, if this term provide another negative number, you will have the positive imaginary part, which say that the fields grow exponentially rather than being decaying. So that's how we show that this quasi-bound state becomes superradiant unstable. So the black hole lose energy, and the fields get trapped between the black holes and the effective potential, and it keep extracting more and more energy out from the black hole. That's basically the superradiant instability. The last part where I like to say, sorry, I know that I'm a bit late now, is the so-called the amplification factor. So basically this factor tells us how much energy being extracted from the black holes. What we are looking at, if this amplification factor set is greater than or being positive, that means the absorption of energies happen. And yeah, we went through a lot of analytic approximation and calculation before we can get this, but eventually we can just show that there are some range of the so this is a plot of the amplification factor against the omega. So the important part is where the set become the positive. That means above the zero line. So that means the superradiance actually happened. And we also check that when set becomes negative, there's no more energy extraction, and the superradiance condition is always satisfied. So okay, I think that's all I like to talk about. Thank you. And I'm sorry for being late for 2 minutes. Okay, questions? Yes, Nase.
Thank you for your nice time and hard working. I'm just worried about if you check the rotating metric is still the solution for the field equation.
There's one paper that's say that if we make some slight modification on the Newman-Jennings algorithm, the solution that you get out of that will always satisfy the Einstein field equation. So that's what we did. But to be honest, we haven't actually solved the Einstein equation itself. We just mentioned that we just study that paper and see that our case is also can be applied for this too. But yeah, we haven't checked it yet. So if you want, you can. Yeah.
You can
Mathematics, huh? Yeah, I know.
Sometimes Newman-Jennings.
Yeah, because normally Newman-Jennings doesn't guarantee that you will get the rotating solution is still the exact solution. Yeah, I know. We will. Yeah, but yeah, we just got rejected this morning. This is very good way to wake up. I got the first email that I say, we're sorry to inform you. Yeah, but anyway, we're gonna do it. Yeah, thanks. Any more questions?
Maybe I
about
the non-rotating solution.
How
many
horizon?
How many horizons?
Just one.
Just one.
Yeah.
So that is asymptotically fat.
Yes. Yeah, now we extend this work, so we try to compute the rest, like shadows, thermodynamics, the same stuff, the routine stuff. yeah, we plan to do this very soon. Yeah. Okay, thank you. I think.
Thank you.
Okay, ขอบคุณครับ
I have a question from
I think maybe one of my students.
online. Online. Okay.
อ๋อแต่
I'm curious. Is
อันไหนตอบคำถาม
to black hole here
This is dark matter.
is a dark matter can collapse.
So basically, what we did, we consider black hole that's surrounded by the dark matter itself. It doesn't mean that you know the dark matter itself collapse and form into the black holes. I think this is my answer. Tem. Okay, I think. Okay, let's move to the next speaker. Okay. So okay, I'm coming back to the chairperson again. The next speaker is Lanchakon. Okay, there. So Lanchakon from Lakabang University, he will talk to us on what? Schwarzschild black holes.
So can you guys hear me?
Yes. Can you hear us?
Oh, yes. I've been
Okay.
hearing you for the whole presentation. Thank you for your very good presentation.
Okay.
APA. Yeah. So now
yeah.
you should be able to see my screen, right?
Yes. Now you have 30 minutes
30.
for the talk.
Okay.
Yeah.
Okay. Right.
Please.
Okay. So I'm sorry I have to talk online like this because I am a bit sick and I'm afraid that I should stay away from you guys. And this is my topic, a bipartite reconstruction of a Schwarzschild black hole. So because I can't use my iPad, so I'm sorry that my slide will be something like this. Actually, there should be a very fancy animation, but now I had to save it into a PDF, so no animation whatsoever. So okay, now the point of this work of mine is that I'm going to try and understand the quantum nature of black holes. So you guys probably know that the thermodynamics of black holes, for example, they contain quantum physics inside it, right? Hawking proved from quantum field theory that there should be something like Hawking temperature, right, from the black hole. Now, that is what I'm going to. That is what I'm trying to do. So let's see what I tried so far. So I'm going to start with the 5-dimensional Schwarzschild black hole, and the reason is that the solution looks easier than 4D actually, and it's thermodynamics. And I'm going to give a bit of a review, actually just a very little bit of a review of qubits and density metrics. And then I'm gonna try to reconstruct the black hole system as qubit systems. And let's see what we will end up. Okay, so now this is the horizon structure of 5-dimensional Schwarzschild black hole. But if you are not familiar with the 5D, you can also like try and recall the 4D Schwarzschild. I'm sorry, it should be Schwarzschild the Sitter black hole. I'm sorry. Okay, so you can try and recall the 4D version of this black hole, which has 2 horizons, the black hole horizons and the cosmological horizons right here and there. Okay, the metric looks like this, and the reason we call it the Sitter is because we have this cosmological constant right here as one of the contribution in this metric. And then there's the mass here, and you can see that there is no number 2 here because right now it's in 5 dimension. The R squared right here, which is supposed to be just 1 over R in 4D. Okay, Now, now for the sake of studying this thing in the fashion that I'm going to do, I'm going to rewrite these two variables into their corresponding length scale. So I'm gonna call this M as RS squared, and then I'm gonna call this bunch, the whole bunch here, the lambda over 6, I'm gonna redefine it as that corresponding length scale, RC, like this. So the final metric will be written like this, something like that. Okay, now, so knowing the horizons, we can actually compute the thermodynamic quantities. For example, the Hawking temperature at the black hole horizon, the Hawking temperature at the cosmological horizon, which I use the subscript here, BH and CH. And then we can also find the entropies as well. The entropy of the black hole horizon, the entropy of the cosmological horizon, which is proportional to the area, or the so-called area law. Now, one more thing is that I haven't given the exact formula for the temperature, but as you know, the temperature here is, well, if the surface gravity of this object is really strong, then you will have a very strong, no, you have a very high temperature as well, because they are a direct proportionality. Okay, so now the point of this slide is that because right now for this black hole, we have two horizons, and that means we will end up with two sets of thermodynamic quantities. We have two temperatures, we have two entropies. So if we want to realize this system as a thermodynamic system, then that means we must be confused, right? We have two temperatures, that's the start. So that's why we are going to realize this system as a two thermal subsystem. So basically I actually will try and look at this as two subsystem which have different temperatures. Okay, and let's see what we will end up if we consider it this way. And yeah, okay. Now, so this is the formula for the temperature. The temperature looks like this. For the black hole horizon, it goes with the plus sign here. For the cosmological horizon, it goes with a negative sign. So that's one thing that you can see, that there must be something wrong with this kind of consideration, right? So if you have you may have positive temperature for the black hole horizon, but you may end up with negative temperature at the cosmological horizon, right? Now, the entropies are like this. So we are considering the 5-dimensional Schwarzschild-de Sitter solution. So the area must be of the free sphere, which is given by this formula. Anyway, pi squared r cubed. And these two are the horizon radii for black hole horizon and the cosmological horizon. So for you guys who have experiences with 4-dimensional Schwarzschild-de Sitter black holes, so you can see that the solutions to the horizon radii are way more complicated than this. Something like that. So this is what I took as an example to test my hypothesis here. Okay, so this looks simple enough. Actually, the only difference is that the black hole horizon has this negative sign or whatever. Anyway, I'm sorry. Now I'm gonna go and do some review on quantum bits or qubits. right? So a qubit is basically a quantum state that can enter only two states, right? Just one or two, or 0 or 1, right? So now in quantum mechanics, we have these quantum state, which can be expressed in two forms. One, you can express it with abstract vectors like the Dirac notation, the bra, the cat thing, like this, right? Or if your state becomes more complicated, for example, if it adopts the classical probability in the system as well, then the better way to state this quantum system is to use the density matrix. So this density matrix here is basically a square matrix. So for example, this is a 2x2 density matrix. And one of the property of this density matrix is that the trace is always 1. And one more thing, the diagonal element of this density matrix represents the probability, the classical probability of finding that particular quantum. Yeah, so that's why should be 1, right? Okay, now, so this is just a brief review of the quantum bits. So once you can specify your quantum bits or quantum states, then you can actually you can actually find its entropy. Now, we have many kinds of entropies in quantum information point of view. The most basic one is von Neumann entropy, which is given by this expression here. You should take the matrix logarithm to the density matrix, times it again, and and then you get the entropy. I believe I forgot the trace symbol here, so that there must be a trace here as well. I'm sorry for my sloppy writing. Or if you are like a bit into quantum information, you may have heard the Renyi entropy, which is given by a little bit of a modification from the von Neumann entropy. So in my case, in this presentation right here, I'm going to use this one, the von Neumann entropy. Okay, now here comes the reconstruction part. So the purpose of this work is to reconstruct a qubit system which represents the Schwarzschild-Sitter black holes. So since we already think that our Schwarzschild-Sitter system can be divided into two thermal subsystems, one with its temperature, right? And then I will try to reconstruct each qubit into the subsystem, each of the subsystem, actually. So to make it more obvious, so we have a black hole horizon system right here, right? With its temperature, with its entropy. I'm gonna try to find the qubit which has the same entropy right here. And then I'm gonna find the other qubit which shares the same entropy as the cosmological horizon subsystem. That's what I'm going to do, and see if there is any possible correlation between the qubits. So because in quantum information theory, we usually study one of the key features, one of the key studies is that we consider the entanglements or quantum interaction between quantum system, right? Okay. Then to do such reconstruction, I'm gonna start with the cosmological horizon subsystem. So this is the horizon radius. which is given by the predetermined, no, I'm sorry, the predefined parameters RC and RS right here. And then the way that the assumption that I used is that if you take a look at this radius, and since we know that the entropy of this subsystem is proportional to R cubed, to this bunch cubed, right? So this thing must maximize somewhere. And when it maximizes, it maximizes at RS equals 0. You can also verify that yourself. Now, since it has its point of like maximum for the entropy, so I'm gonna try to find a qubit which maximizes its entropy when it comes to some kind of condition. So one can find the qubit by, let's say, if you model a qubit by a density matrix, so your density matrix can have all kinds of matrix elements, right? Except that you only have to make your trace to be equal to 1. So that is your only restriction, right? But after that, you can find all kinds of density matrix. Now, there is one form of density matrix which has the maximum entropy, which is this form. This form, the density matrix is diagonal, and the diagonal elements are equally distributed. So if this density matrix has n dimension, and then the diagonal elements will be like equally distributed to be 1 over n. So this form of density matrix will give the maximum entropy. So since this form gives maximum entropy, and when you take RS to 0, your cosmological horizon entropy is maximized, then I'm gonna identify these two systems with entropy, just like this. So basically, it means that when the cosmological horizon entropy is maximized, it should be described by this kind of density matrix with the rho CH max here, the green one. So it turns out that if we do that, then it means we can actually identify the number of states here, the n, the number of dimensions or the number of quantum states. We can actually identify it with some formula in terms of RC, or actually in terms of the cosmological constant. So what turns out to be is that the they are not direct proportionality, but you can see that if your RC is big, then your n is also big as well. And if your RC is big, then that means your cosmological constant is small. So basically, this RC is the length scale. So if you have our length scale, no, I mean the length scale for the cosmological constant in our universe is big, which is why the value of the cosmological constant itself is small. So big RC give rise to big N. So if this is the limitation of my calculation and my tools, so I'm gonna choose to consider only the case when n, this n here is 2. So basically, I'm gonna consider the qubit version, just two quantum state object in this case. So that's why I chose 2 here to be our starting point. And of course, if I chose n equals 2 here, since n is closely related to the length scale of the cosmological constant of our universe, then that means if I choose n equals 2, then that, of course, shouldn't reflects the realistic universe? Yes, of course. And I will have a say about that in the very last of the presentation. So let's keep that in mind. Now, so when n equals 2, then we are talking about the 2x2 density matrix for the qubits. And I'm going to require that this density matrix, the density matrix for the cosmological horizon subsystem, should be maximized when Rs equals to 0. So basically, I'm going to identify the point of maximum entropy for each systems, right, into one, and join them together. So by having 2x2 density matrix, you will have a diagonal elements equally distributed. So basically 1/2 and 1/2 on the diagonal elements. Oh, and I may have forgot to mention that all of the off-diagonal elements are 0. So there are only diagonal elements here being equally distributed, while the others are 0. Okay, so we'll have 1/2 and 1/2 on the diagonal elements and 0 elsewhere. So if this is the state of maximized entropy, then if I introduce some certain function that depends on Rs, like this, then probably I can identify the entropy of the CH subsystem with this kind of density matrix everywhere away from Rs equals 0. So this is what I assume. Now, this is what we require, and then we require that the black hole entropies, the cosmological horizon entropy must be equal to the entropy corresponding to this density matrix everywhere for all values of Rs. And since the von Neumann entropy contains the matrix logarithm, that is the main problem to almost everyone, as I heard, who study quantum information. When you see a log, then that means it's very difficult to find the analytic solution. So that's why we will compute this numerically. So I actually have to, I can't show you any analytical solution here. I only can show you graphs, which comes later. Now, we will do the same thing with the black hole horizon subsystem. So we will start with the diagonal elements with equally distributed, like 1/2 and 1/2 here, and modify it a bit for any value of Rs away from Rs equals 0. We will model it the same way because we all know that the cosmological horizon is, of course, bigger than the black hole horizon, as we can see from the graph previously. And if this kind of density matrix can identify its entropy with the entropy of the cosmological subsystem anywhere or for all values of Rs, then that also means this form of density matrix must also be able to be identified with the entropy of the black hole subsystem as well. Just like that. And then we do the same thing here. So once we do that, we will end up with the density matrix for the BH and the density matrix for CH, which is given by different functions here, a G and an F. So yeah, right. So what I'm going to do next is that I'm going to correlate these two qubits together, because my assumption is like this: a Schwarzschild zeta black hole like the two subsystems inside it coexist together. So what I'm going to do is that I'm going to see if once we correlate the qubits, then is there any possible way to study the correlation between these two horizons or not? And actually, my first hope is that I should be able to see some quantum interaction, something like that. Okay, now here comes a little bit of a problem. So once we try to correlate the BH subsystem and CH subsystem, mathematically speaking, we are going to find the total density matrix like this. So the total density matrix must be of the dimension of that from BH subsystem multiplied with that of the CH subsystem. So in this case, 2 times 2 equals 4, and we should end up with 4 by 4 density matrix. And to make this density matrix actually the total density matrix, which contains the BH subsystem as well as the CH subsystem, we should be able to do the partial trace of the total density matrix. If we do the partial trace is like, if we are talking about high energy physics, then it's like integrating one of the degree of freedom out, just like that. In this case, it's like we sum all of the possible outcomes of the other qubit, which we don't care, out. That's what we call the partial trace. So if we partial trace the total density matrix, by partial tracing the CH out, we should end up with the density matrix of BH. And vice versa, it should be the same, right? Okay, now the problem is that, oh, this is a bit sloppy. Anyway, so the problem is that it's not unique. So even though I have the reduced density matrix like rho BH and rho CH, even though I have these, even though I can construct some kind of a total density matrix whose partial traces give the smaller density matrices, yes, but it turns out that there are actually many and many ways to construct the total density matrix whose partial traces are just like what we want. There are so many ways. So to construct, I'm going to follow these steps actually. So this is one way to construct by just use those density matrices and tensor product them like head on like this, and then you will get a total density matrix. This is one of the ways that we can get the total density matrix out of those two smaller density matrices. Or actually an and here, but I'm going to talk about the context of many ways how to construct this, right? Or you can start with this and rotate it or transform it with appropriate operators. So there are non-local operators here, which is introduced by this the paper of this guy, Omar Gamel. I forgot to include his archive number in the slide. I'm really sorry. So so as you can see now, there are many ways to construct the total density matrix, which gives out the partial traces to be what we want. By okay, the first candidate is this guy, right? The direct tensor product of the twos, or this one and transform it into the other thing. So now, how can we choose then? We can choose that. Yes, of course, we can choose such thing that when we transform it, we still require that the partial traces of the transform density matrix must return the smaller density matrix. So now you can see that I have a bar on my density matrices right here. So this is to show, this is for, because I'm using the row CH here in too many places, so that's why I have to distinguish them with bar and non-bar here. So I'm gonna start with this, but then I'm gonna rotate it into a not bar density matrix, and then I'm gonna require that the partial trace of this thing will be just what we obtained from the very beginning. Now, one thing that I might have to mention is that when we transform this density matrix from something to something else, then the partial traces of the transform density matrix give you different results. So the partial trace is somehow not, what's the word, covariant with this transformation. I believe I used the correct word. So this is what we do. So first, we try to construct a product state by direct tensor product of these two, and then we rotate it a bit with non-local operators, and then find a partial trace. So the partial trace will actually not be the same as what we start with. So it's like this. If you start with number 1 and you do the partial trace right away, then you will end up with the density matrix of BH bar and the density matrix of CH bar. But once you rotate it and do the partial trace later, then you will end up with different things. And we are going to require this, the density matrix of the system drew by this purple chalk thing here that I did with the row BH without bar. Okay. So as I said, there are many ways to construct this. So the limitation of constructing this is 1, this inequality. So for quantum system, you can always correlate two quantum systems together as long as it doesn't violate this inequality. Now, the upper bound is the maximum classical correlation limit. So when you have two subsystems and you correlate them together, but in a very dumb way, for example, just place them together, so the entropies are added. That's the maximum bound. But the minimum bound here is actually the subtraction of the bigger one, of the bigger entropy with a smaller entropy, and this is when our correlation enters the quantum regime. So as long as your density matrix obeys this thing, then it will be fine. That's one restriction. Now, the other restriction is that it doesn't mean that when you construct a density matrix, you will end up with physical matrix. What I mean is that if you remember what I said earlier about the density matrix, the diagonal elements represent the classical probabilities, right? So there are two conditions on those classical probabilities. One, the summation of the classical probability, the summation of the classical probabilities must be 1. And 2, the classical probabilities must be like physical probabilities, right? So basically it should be positive. So in the paper I suggested, he also introduced a way to check the positivity of the density matrix as well. So once we do that, we will see that in this case, if we are trying to reconstruct the qubit system with the reconstructed qubit system to be like similar to the Schwarzschild-de Sitter black hole, then the qubits, the qubit system cannot achieve this how to say, lower bound of the entropy here. It will be something else. So it means that it's just like there must be some kind of constraint that that kind of putting this bound more stringent. That's what we found so far. And this is what I meant. So this graph shows the possible ways of correlating the subsystems so that the entropies will be these denoted here. So if you started with okay, let's start with each line. So these black dotted line represents the SCH. So this is the system of two qubits where there is certain correlation so that the total entropy is just that of the cosmological horizon. Now this is the lower bound of the classically allowed correlation. So it's just like when you have not sure. Yeah, I think it's just like when you have two coins and then you just strap them together with duct tape, for example, and then you just toss them around. You will end up with the same entropy, right? The same number of outcomes and then the same entropy. Now, this is basically that kind of situation where you kind of correlate the two subsystems, and then the total entropy will be that of the bigger system. Now, if you go down to these blue dotted line, this is the quantum mechanically allowed correlation. It's the lower bound.
Not 5 minutes.
5 minutes. Okay, I need to be quick. I'm sorry. Okay. So if you want to correlate it in a quantum way, then this is this is how far you can go for the entropy. This is how small you can go for the entropy. Now, what we come up with, our result is that our black hole qubit reconstruction system cannot achieve this line. Somehow it is constrained so that it can only achieve this red line. It can't go further. It can't go down. It can have all kinds of correlation upwards, but not downwards. Okay. Now, this is the result for n equals 2 qubit reconstruction. And it seems like we are talking about qubits, and if that qubit somehow represents some effect from the gravitation side, and then we may that's why we can see this red line, which is not the blue line, right? So somehow the gravitational effect plays the role here. Now, what kind of gravitational effects that plays the role here? To be honest, we really don't know yet. So this is what we plan to do next. And the first one we tried already, but the next one, the second one, and the third one is that we are also trying to to do the same reconstruction of the Reisner-Nordstrom black hole as well, because you know, the Schwarzschild-de-Sitter black hole can be quite a very extreme example, because the cosmological horizon can be really big. So in our universe, then this cosmological horizon should be really far. So the correlation between them can be not so big, right? And this is a new idea, which I really don't have an idea about it. One of my colleagues, P.O.M., Dr. Thanapat, just suggested me one day, and I'm going to see what this is about later, but very soon. Now, about the first one, about what we already did, we can use the 2-qubit state, 2-qubit density matrix. We can use that and try and enlarge our reconstruction to be n pairs of qubits. So the way that we did is that we just take the density matrix, the 4x4, which represents the 2-qubit, and then somehow just do a straightforward tensor product of these rows. We just prepare n copies of rows, and then just tensor product these things into a very big density matrix, and then we tweak the parameters a bit so that we end up with a big Schwarzschild black hole. We can actually do that in principle, and then this generalization actually is a very straightforward. So it doesn't introduce any kind of interaction between the pairs. Well, we have interactions inside the pairs, but we don't have the interaction across pairs. So that means we can actually embrace these results that we can get from the n equals 2 qubit system. So this is one way to generalize it, but of course there are other ways as well, of which we will continue this in the future, very near future. And I believe that's it for my presentation.
Quick question.
Hello. So, when you are constructing the bipartite states, you are just using tensor products. Then does that mean that they are separable states?
Yes. Do you mean the generalization into big black hole?
No. It's the yeah.
I see.
So you're using tensor product for 2 qubits. So you're assuming that there isn't any quantum correlations or entanglements between both of the entropies, or like the two horizons you're mentioning.
Okay. Yes, if you start with the tensor product of these density matrices, then of course there is no quantum interaction or no entanglement. There is none, actually. But the non-local operator that is expressed in this guy's work actually introduces the entanglement. So, well, there are two kinds of operators that can transform the density matrix. The one kind is that you transform it so that you are changing the basis of each of the density matrices. That's one kind, which is called local operator, if I remember correctly. But the other is to mix the elements of these two density matrices in a very non-trivial way, and that is called non-local operators. And this is what introduces the entanglement between the two. actually. So basically, we are considering the entanglement between the two sectors already with this non-local operator. Because partial tracing is not, I mean, if you do partial trace before transforming, you get one result. If you do the partial tracing after the transformation, you will get the other result entirely. You will get different entropies for each of the bipartite subsystems. You will get different kind of correlations as well. So all of the correlations or entanglements are introduced through this non-local operator here.
Oh, okay. I didn't catch the non-local operator. Okay, now I understand.
Okay, like there's something very basic that I don't really understand. So like, you said earlier that like you set the qubit to have the same entropy as the black hole and the cosmic horizons. I don't understand like why do the qubit has to have the same entropy?
That's one way of identification. Well, at first, well, I know how to find the entropy of a qubit, and I know how to find the entropy of the black hole horizon. Then that's my first motivation. And secondly, well, I think it's well, you know what? I really don't know.
Yeah, like because if you put it in the black hole, it should have the same temperature, right? It's not the entropy. I think it should be temperature if you put it there. But I think it's if you put the qubit, like many qubits, maybe the system itself become black hole. I think I thought that you mean that, yeah.
Oh, well, as far as I know, if you want to find the temperature corresponding to a qubit system, it's way bigger. No, it's way complicated. Well, you need to have a density matrix first. Like you need to know all the elements of the density matrix, and then you need to put an assumption that this density matrix is some kind of a canonical thermal state, right? And then you can just write down, you can just diagonalize it and write down the, how to call it, Boltzmann factor or something like that, the exponential to the beta t, the exponential to the negative beta energy, something like that. So you need to do that. So if you start with the temperature, then you're gonna need to know the density matrix beforehand. That's what's that might be because that might be the reason I didn't try this, because you need to know a lot of information before you can find the temperature. But right now, if you know the density matrix right now, then you can actually find the temperature. And so right now, actually, we can actually find the temperature. We can actually find the temperature as well as the energy eigenstate, I think, because we know the density matrix already. And then if we assume that this thing is a canonical thermal state, then yeah, this thing has this Boltzmann factor, and you can solve for T and energy eigenstate. That's what I believe we can do for now.
But like at least it is not, the state is not qubit, right? Like this should be more like state, like the state for the black hole and for the cosmic horizons. I think it's too naive to think about to represent it as a qubit. So yeah. Yeah. I think I'm not really understand, like, yeah.
Well, you can just keep asking. I mean, let.
Yeah, okay.
Oh, that's it.
I think that's
Yeah, there's one more.
Okay.
I have a question. You say that cosmological horizon have an entropy. I just started learning a bit of information theory. Is entropy come from that we don't know some information in that system, we're missing something, so the uncertainty appear? Is it what uncertainty appear from cosmological horizon? Is it because we don't know what outside of that horizon, so it have entropy?
That's what I thought as well when I heard this question. Yeah, so maybe that, right? Maybe that, because if you think of the space-time structure of the Schwarzschild-Sitter metric. Now, where is the space-time structure? This, right? So yeah, I think it works in the same way as the black hole horizon. You don't know anything inside the black hole horizon from the outside perspective, right? So that's why it gives rise to entropies, because of uncertainties that you feel. And I think it works the same way as well for the cosmological horizon. You can't go beyond the cosmological horizon, I think.
Another thing, when you mention parameter R, and you want to make a uniform distribution 1/n, right, for a density matrix. If R is related to 1/n and n is a discrete amount, does this mean your R parameter is also discrete?
Yes, it appears so.
What did this mean?
That's one of the questions that I have, and I don't have the answer for that, to be honest. But yes, it also means that if this reconstruction is somehow the truth of the universe, then it means the lambda must be discrete. Yes. But I don't have the answer for that question. I'm sorry.
Thank you.
Lambda means cosmological constant, right?
Yeah.
Oh, okay.
So just a little bit more. Maybe I need a bit of clarification from you, because extended from my previous question, you treated the state as separable first. So then you apply this non-local operator. So I'm not very familiar with black holes, but do we assume that first the two horizons, they are actually separable, then something physical mechanism that can be modeled by the non-local operator happens, then it starts mixing together, having some correlations.
Yeah, just like what you said. But I don't mean for this process to happen over time. Like I didn't mean for this to happen at like steps. So it's not like black hole starts like this. It's like our math computation starts here, and then we're gonna in my opinion, I'm gonna call whatever we have at this point a reconstruction of black holes right here. But right there is just trying to do math. something like that. So that is, I don't mean this to be something like a dynamic from having a separable black hole or something like that, and somehow it evolves into a correlated black hole with some certain physical phenomena. I didn't mean it like that. I kind of started it with a bunch of math right here, and then I'm gonna call whatever is the result a black hole, something like that.
Oh, okay. Understandable. Thank you.
ครับ
Yeah, about my last question. So like, yeah, okay, okay. So like, you use qubit, right? I still don't really understand why you use qubit. Can you explain it again? Like, I mean, can we really just decide the dimensions of the density operator by ourselves to be in is equal to 2, or like it should determine by like the system?
Okay, to be honest, the math is easier. Like, this is an assumption, right? I mean, this idea, this whole idea of mine is just an assumption, and we were trying to see if this assumption works or not. So that's why I'm gonna stick with the qubit, because n equals 2 is the lowest dimension that you can have for the density matrix to, you know, yeah, something like that. So that's why a qubit. Of course, you can try with a three quantum state object, q trip or q quad, I don't know, but that case the math is way more horrible, actually.
Okay.
So
yeah. Are you coming back to our school someday? Like,
I will, because I'm gonna catch my taxi there, but I actually am afraid that you guys might hate to discuss with me because I now have a cold.
Oh, okay.
Yeah, right.
Okay, firstly, for me, not hey, not sorry. Yeah, not. I have one comment that it's possible that we have non-local operator that better than this paper. Yeah, have you looking for other non-local operator? Is possible?
Not sure, ครับ I'm not sure. When I was doing this work, I kept searching for all the things that seems to be involved. Yes, but I really don't know if there is any other more general. You mean more general non-local operators or those things, right, Ping Wong?
Yeah, thank you for an answer for the last question. Yeah, really. yeah. I just think. Yeah, I just think about Naresuan limit. Yeah, Naresuan limit is the saturation of the black hole mass. That's the limit that we have the equal value of event horizon and cosmic horizon, right? And I think that if we have the quantum correction or quantum description of this system, when the black hole horizon saturate at the same as cosmic horizon, actually Naresuan limit is from classically, right? But if we think that it have the same size of the cosmic horizon and black hole horizon, is it possible that uncertainty principle or some mechanism from quantum can change the Naresuan limit? Yeah, have you think about that before? Have you thought about it before?
No, so far, Ping Wong. So maybe we can talk later and maybe we can come up with something, Ping Wong, maybe. Because well, in this module, then you can actually achieve the Naresuan limit or the extremal limit as well. And so far there is no such thing because I maybe haven't considered it. But yeah, it might be very interesting ครับ to consider it at that limit ครับ
Okay. One question after last question. Sorry. Yeah, I think linear nostrum black hole is quite difficult to represent it by 1 qubit, right? Because at zero temperature is still have entropy. So what do you think about linear nostrum? Is should have more than 1 qubit or not?
Well, actually, the model so far is represented by 2 qubits. We have 1 qubit for the black hole horizon. We have the other for the cosmological horizon, and then we correlate them into one single quantum system. But inside it, we have 2. So for the case of Rhino Nostrum, then we have the inner horizon as well as the outer horizon. So 1 qubit is for the inner, the other is for the outer. Just like that, ครับ Ping Wong. But the point that you said, the extremal limit of it doesn't I mean like the entropy. Oh yeah, right. The entropy of it is not 0, right? That might be a very
The problem quite more complicated. Yeah, but you should use more qubits. But I think the problem is that it's quite more difficult to do calculations like. Yeah,
Yes.
but I give some news that nowadays it's possible to access quantum computer. Yeah, better. Yeah, by my student access more. Yeah, better. Yeah, you can consider to use more qubits and learn about some quantum algorithm and to send the code to quantum computer directly. Yeah.
I see.
Okay.
I see.
Just comment. Yeah.
ครับ Thank you ครับ Ping Wong.
Okay, let's thank the speaker again. Thank you very much, Nod.
ครับ
And I hope you get well soon. And are you going back to Bangkok today, right?
Yes, right. I'm flying.
Okay, safe trip. I'll see you. Bye. Okay, for us, let me make some quick announcements. So we will have lunch here at the same place before we go to the excursion. However, after the excursion, there will be no dinner. So you guys have to be responsible for your own dinner. But the organizer suggests that there will be the street food inside the university, ตลาดนัด or some sort. Yeah. So maybe after you went out for the excursion, you can come back and enjoy street food in the university. And tomorrow we'll be back here again, same time, same place. Okay. Yeah. Go ahead. We can have lunch now.